then the next one the same distance over, moving at the same speed away from that, would be 100% shifted.
Coming towards us?
Why? No, it can't come toward us.
Just as a wee thing, I lifted up my phone and by accident unlocking the keypad, I locked it again and then unlocked it again, and it rang emergency services that I had to ring up on. So if the police arrive at the door or an ambulance arrives at the door, that's why.
You should go ahead and call them now and tell them that you butt dialed.
Yeah, they're ringing me back.
Yeah, okay.
Right.
Because they're going to call you back.
Redshift is only relevant to an observer.
Yes. Okay. So we're raising. Let's say we're raising number 1 for this example, and I have to switch us to raising number 3 later.
Okay. Why do we need to go more than 2? I know it sounds, but you go on. It doesn't matter. Go on. I was trying to simplify.
Okay.
But go on.
Well, okay. So if we're in raising position number 1, right? And say Andromeda is raising position 2.
Right. Oh, I get you now. Got you. Yeah.
And let's say that the next galaxy over that I don't know the name of is raising position 3.
Yeah.
Okay, if we were at position 2, then positions 1 and 3 are equally moving away from us, just for example.
Yes.
Okay. But they're also simultaneously moving away from each other, yes?
Yes.
Okay, so they can't maintain a distance while in the middle the distance is not maintained. If it's expanding in the middle, it's expanding everywhere, right?
Yes.
Okay. So back to position 1. If at position 1, position 2 appears to be 50% shifted of the light spectrum.
Yes.
And position 3 is moving equally away from that, then it's moving away from us twice as fast as it is from position 2.
You're misjudging perspective.
Yes. No. Well, no.
No, I'm not.
You're right that it's moving twice as fast.
Okay. So it should be shifted more.
Yes, it is.
Okay. All right. So just in this example right now from perspective, we're at position 1.
Are we 1 or are we 2? This is where I'm watching.
We're 1.
That's what I was going back to. We're at position 1.
Right.
Let's say we observe position 2 at like 0.33 redshift.
Right.
But then position number 3 should be at 0.66 if they're all moving equally away from each other.
Yes.
And we do see that.
Yes.
Okay. Where does the redshift go into the infrared spectrum and out of the visible light spectrum?
What do you mean?
Okay, so let's say it was 50% of the scale. What's that?
The whole spectrum is moving up. It doesn't. We call it redshift because that's how we observe. But all light, the entire light spectrum, is being stretched.
Yes, I understand that.
Okay.
But light spectrum is only visible within light spectrum.
No, light spectrum is from microwaves to
no.
X-ray. Yes.
He's talking about visible light.
No, electromagnetic spectrum is from all the way to ultraviolet.
All right, you're talking about visible. Forget visible.
Well, when we say redshift, are we talking about visible light or not?
No, it's been moved to the redshift as an infrared. It's been taken from what it was sent out and shifted towards the red end of the spectrum. Not that it is.
You can't.
I think everything I've said already indicates I know that.
Yeah. You can't talk. You're right. Right. The problem is you can't talk about when you're talking about any of this stuff. You are not talking about visible light. Visible light is just the bit we see. Right. Redshift, the cosmic microwave background, which is microwave, is still the light from stars and photons that would have been a certain frequency back then, but it's now in the microwave spectrum because it's been so far away. Because the universe has expanded so much since it was released. Right. Okay. It's never about visible light.
Okay, I was trying to keep it simple within the mind frame that I have in my objection. Okay, I'll use the whole scale. Let me go ahead and use the whole scale then. So let's say if we were traveling along beside of position 2, we would see white light.
For example, okay, go on.
Coming from a star that produces some kind of white light. We would see it.
Yes.
If we were simultaneously moving the same way at the same time.
Yes.
Okay, but because we're at position 1, it looks shifted to us. It looks shifted toward the red end of the spectrum.
Right. Okay. Yes. But you're
That sounds like a tentative
negating
yes.
time from the equation here.
Why am I removing time from the equation?
Because you couldn't look at it at the same time we are.
I didn't say that. Time and distance would be a necessity of the total theory.
My point being that the light that they would be seeing would be light that was released billions of years ago when everything was when the universe was less expanded.
So when you said it was losing energy over time and we don't know where that is, where it's going or how it's being released, now you're referring back to that and saying I made a time reference. And you're right, you did.
I'm saying that you're trying to compare two events. You're trying to compare an event where we witnessed light, say around being released by our sun, and that light being and the similar light being received in another galaxy or another raisin away.
I didn't take time out of the equation. I don't know why you're saying that. I don't get it. Maybe I'm really, really, really lost.
Because you're trying to. Well, okay. The problem is I'm trying to think a step ahead of you. It seems like you're trying to understand how the light can be stretched differently to different places.
Nope, not my point at all. It totally makes sense that it should be.
Okay, go on. Keep going.
I mean, now you're just talking about basic Doppler effect.
No.
Okay, why not? Time over distance, stretching the wave, loses energy over distance into space matter, etc. And you get a weaker signal that is more stretched out because of your position and relative speed. What's the problem?
I don't think I've never considered trying to use Doppler to explain the expansion of the universe as to what it does to light. They do. No, they don't.
No, actually, it was Doppler's student who came up with the theory of redshift.
But not.
And when they teach it using the Doppler effect, and in the definition of it, they include the Doppler effect.
Because Doppler is used. Because Doppler is used for a different thing. Okay, they talk about two different things. Okay, and you're right. It can get confusing in astrophysics and in astronomy and I can't remember the name of the field. They use Doppler and redshift when talking about measuring the distance to stars and movement of stars and speed of stars, right? They use redshift all over the place. Okay, and then they use the Doppler to talk about it because that's how it's relevant. When they're talking about redshift to do with the expanding of the universe, it is a very different thing.
Okay, would you like to explain to me the difference where I'm confused?
Because, oddly enough, it's the same, similar consequence, which is why, right? Because when you get the light from, let's go with a pair of binaries, a binary star system.
Okay.
Okay. Now, from the light coming off that, they can tell you which star is moving towards us at that moment in time and away from us.
Fair enough.
Okay. Based upon the amount that the light is shifted towards the red or the blue.
If the plane of it, and if we're looking at the side of the plane of it,
yes,
sure.
If we're looking at the side, yes. Okay. That's one of the main ways Doppler is used to and we have now got it precise enough that we can use that to show a star. A spinning object, a star that's I don't know if we can go as small as a neutron star, but something the size of our sun, we can measure the distance and speed between the sides of the star to work out which way to how it's rotating and the speed it's rotating, and it's all calculatable.
Sure, I imagine why. Yeah.
Right. Okay. Now, redshift, to do with the expansion of the universe, is literally, it's just a photon of light, a wave of, or I think the way you get a photon or a wave at this point to describe it, but you have light that is traveling across empty space, and the space gets bigger.
Yeah.
That's it.
Yeah.
Got nothing to do with the speed it's moving at, with what released it, about anything. It's just the space gets bigger, so the thing that's in it gets bigger.
Part of the theory of the redshift is how much it is redshift is the speed.
I don't understand that sentence.
Okay. If you look up bright stellar objects redshift, you'll find there's a different metric. There's the same metric giving different indicators. Some are redshifted less, some are redshifted more.
Yes.
It's because there's a scale of how much it's redshifted.
Yes.
Because it's redshifted differently, and part of the understanding of what's going on is that indicates which way it's moving and how fast.
Not to do with not to do with the expansion of the universe.
What do you mean not to do with the expansion of the universe?
That what you just described is using the Doppler, the Doppler equivalent to measure stellar to determine things about the locality of stellar objects.
No, I just said the movement of stellar objects, not the locale.
Right, but my point is we're talking about light once it's been released.
Right.
Right, light once it's been released is not subject to Doppler in any way.
Right, you need a continuous light source changing over time to get that.
Right. Yes, right. The light that's been released that is redshifted by the expansion of the universe is light that is in transit.
Right.
Okay? The wavelength of that light gets changed in transit.
I have found what you were trying to show me. Thank you.
There we go. It's the in transit bit, isn't it?
The actual thing that it is moving through is being
Good job.
stretched, and as a the thing is being transferred through, it gets stretched as well.
Does that make
Fair
sense?
enough. Oh yeah, it's totally good. I found the whole. You found the whole. Thank you.
Is Nerdy coming up?
Doesn't look
So I
like it.
can be quiet. I don't know who you are. This is why I ended up putting Dave after my name.
Who? Big Zebra?
You mean me? I didn't put Richard behind my name?
No, it just says demolished.
No,
Doctor.
someone says, who is Demolished Doctor, and he looks very like Richard Madsen.
Oh, you know
Whilst-
Big
Yes,
Zebra.
a lot. Yeah.
Look,
He does.
yeah,
Very similar.
We're not identical twins. We're exactly the same human being.
yeah. No, Richard's identical twin is Flat Earth Aussie Jesus with out the beard being dyed. BigZebra.com is Steve Bowden.
MathPig, onto your previous points about... Oh, he's muted. Unmute yourself.
I have been fucking muted the whole time. Richard's
I
exact
thought you'd be
twin.
quiet.
Richard's exact twin is Flat Earth Aussie Jesus without the dye pack, and
That dude doesn't look anything like me, man.
and BigZebra.com is Steve Bowden. Look at the icon. Yeah, I knew it was Steve Bowden. That's what I meant to say. Is Big Zebra, Big Zebra? I meant to say Steve Bowden. It's the icon. He's a zebra. Where Nerdy's a rodent and I'm a pig, he's a zebra.
We're a positive zoo.
Well, he joined the Discord, I think, as Big Zebra.
Did he?
He's something zebra in the Discord. No, you wouldn't ruin my scene, look. It's as simple as just doing that, Nerdy. Now you're welcome.
What the hell did we get that scene? We didn't
Because-
start with that scene.
No, you didn't start with that scene. I led you in and then you just got into your bits and bobs and then I just did it. I need fucking arguments from a playlist, man. I'm going to snippet that just a wee bit, put it into the argument section. Nerdy, come on up. Sammy, come on up. Steve Bowden, come on up to fuck, like. Anybody's welcome, like. Another question that was answered in the chat is we all want more Dave.
Do we?
We all want
pretty
more
much.
Dave. Yeah, definitely want more Dave. I think Dave should start doing little guest appearances, maybe once a week, either a Sunday or a Tuesday. Yeah. I don't want to give up my entire show to somebody else. I've got Thursdays with Richard, and then but I'll have one day with me, one day with Dave, and one day with Richard. I think that's the three people on screen are now the MathPig show.
So I've been thinking about what you said, Dave, and I think my objection still is valid.
Go on.
Okay, even though I never got to it.
No, you didn't. So I don't know what it was.
Yeah, right. Well, we just didn't get to it. There was other things we had to hash out. Okay, so I feel silly talking about raisins, but what the heck? We'll just call it raisin points. From
Richard, I actually named the video what it was called before, and then We Talk the Universe, or We Talk Something, and Raisin Bread.
And Raisin Bread.
So, yeah.
Okay, so Raisin Bread, which is delicious, by the way. Objectively, it's not an opinion. Okay, so in raisin position 1, when I view raisin position 2, because space is expanding between positions 1 and 2, then it stretches out the light as it is stretching that amount of space.
Yes.
And that should be equivalent to the space expansion.
Yeah, well, it is the space expansion, but yes.
Okay. This is the first time I've looked at it this way, so I'm experimenting and asking for objections and verifications.
Okay.
Okay. So between positions 2 and 3, the same equivalent thing is happening.
Yes.
Okay. So viewing 3 from 1, I should see if they were perfectly equidistant in a straight line, going equally away from each other. Okay, all the impossible stuff taken for granted without making those adjustments. What I should see is twice the redshift.
Yes.
At twice the distance.
Yes.
Okay. So if I use the entirety of the electromagnetic scale as we know it, as we can measure it, and let's say that 1/16 of the scale were used between positions 1 and 2.
Yes.
Then twice that amount, or 1/8, would be used by the time I got to position 3.
Yes.
And if I went to position 6,
Yes.
I'm not that good at math. So if I went to position 4, then I should have let's see, 1/8, 1/4 plus an eighth. I should have 3/8 of the scale now disposed of.
Yes.
Okay, so there's a limit to that.
Yes. Till all the energy is dissipated.
In which case, I have no scale left.
Yes.
Okay, so what is that distance? And do we apparently see beyond that, or are we falling short of that distance?
I can't tell you. I don't know, though, the answer to those questions. I can tell you what we talk about in the future. Okay? It is said that we live in a very lucky time in our universe.
I've heard this, yeah.
Okay? Because of what we can see.
I've listened to Krauss explain this. Keep going.
Right? And one of the things is the cosmic microwave background. Because the cosmic microwave background is going to get dimmer and dimmer
until you
and
cannot
then
see
fade
it
away completely. Right? And that is because the things that are giving it off that we would still be able to see will be too far away. So the light, the energy from there, the light that was released by those objects will have dissipated.
And the energy at, what is it, 2.5 degrees Kelvin will have dissipated. Keep going.
Yes. Yeah. I mean, that's also the reason at the moment that no black hole, we don't think we will observe any black holes evaporating.
Right.
Because the cosmic microwave background is feeding them all. Until the cosmic microwave background goes away, a black hole probably won't ever evaporate. No, a non-mass created one will never evaporate.
Okay.
So
we're in a lucky time.
What?
So we're in a lucky time.
Yes, well, that's it. The fact that we can see it, but like I said, I don't know the answer to your question. All I can say is that what they've said about the cosmic microwave background is it's just going to keep dimming as it gets stretched further and further.
Yeah, that would be part of it.
Until that's it. Until it reaches the point where we can no longer detect it.
Okay.
That's it. The light, the energy will be lost. I don't know what distance that is. I don't know how long that is. I've never particularly looked into it. I mean, it's a long. It's taken this long. It's taken 14 odd billion years to get to microwave.
Right.
What comes after microwave is at the bottom of the spectrum.
As far as I know, just really long microwave is the bottom of the spectrum. Now, there might be more beyond that. We just don't know and haven't tested for it. But it might be like periodic table where you run out of spaces. I don't know which one it is.
Where do we go?
Pardon, Dave? What'd you say, Dave?
So I'm gonna have to look into the redshift and where it drops off the scale, and if we see beyond that in redshifted electromagnetic spectrum, to know if, because you only get half the scale to start with.
Why?
Oh, where are the purple lights out there?
Everywhere.
There are purple lights out there.
It's ultraviolet. We can't see it, but we can detect it.
Okay, so starting at I guess gamma and working your way down. There are things producing X-ray gamma rays. Yeah, never mind. I'll shut up now.
I mean, when we discovered these things, it was mind-blowing.
No, I've seen the maps. Yeah.
I mean, do you understand what the ultraviolet catastrophe is?
The ultraviolet word I couldn't understand.
The ultraviolet paradox, I think. Catastrophe is something different. Right. If
the ultraviolet paradox. Let me see if I can guess what it is.
Go
on. Nope, not going to guess it. Go ahead and tell me.
I'm probably getting the name wrong. That's the worst thing. Right.
We'll deal with that later.
Right.
No, the more you talk about it, you'll remember. Just keep going.
I know. Right. If the universe wasn't expanding, and we didn't have the redshift because of the expansion,
right,
the sky would always be white, day and night, because every direction we can see is a star. Every pinprick, you take it down to a millimeter at each point, there is a star at some point in the past.
Sure.
So the sky would always be white. It would be brilliant white all the time.
Wait. What if it started far away and is spreading out enough that it appears black to us from here right now? It wouldn't be all white.
If it started right now, no.
No. If it was always that far away.
But it would have been...
If the universe was static. No,
yes.
Because the light... No, okay, if the universe was static...
Yeah.
Okay, which I'm fairly certain when they came up with this problem, it was. But we'll come to that. Right? If the universe was static and the universe is as old as it is now, we would still have the light from that far back.
It wouldn't have stretched. It wouldn't be outside.
So that light would have been emitted 14 billion years ago.
Okay, wait a minute. Wait. Is light a particle or a wave? Because
sod off.
No.
Because if it's a particle,
Richard,
the particles get further away from each other over distance. You could have a black spot that's not black.
That's quantum mechanics. That's
technically speaking, you're right, but it wouldn't matter because there would be another star that would fill that spot.
That depends on how far away they are.
In the visible universe, it would fill every spot. One thing I remember from childhood is one of the TV shows as a kid, as a science show, it said, "You want to build a time? You want to look back in time and they told you to go and lift a toilet roll, the inside of the toilet roll, and look at the night sky, because you are looking at light that has left so long ago. And it is dark, but if it didn't, as Dave says, it would be white everywhere. It wouldn't have shifted outside of the visible spectrum into the infrared. It would still be in the visible spectrum.
Have you seen the mathematical models about forests?
That's,
If you stand in the middle of a forest, you cannot see any path out. You will always hit a tree.
yeah,
I understand the idea. Yeah.
I understand.
Right,
it
it's
as
the same. And I'm sure that's got a name as well, but I can't remember it.
I think that's not a very good way to explain this to me,
Fair enough.
because that's really easy to show doesn't apply.
No, it does apply.
I think what Dave's
No, it
trying to
doesn't.
say is if you walk in a straight line anywhere, ignoring time, there is always something in that position. You'll always bump into something. You can't go in a straight
Yeah.
line from the center of a forest and walk out without hitting something.
I get that.
It's the
But
same with stars.
what you're talking about now is the size of my eyeball, which from where I am, the size of my eyeball is 16 light minutes.
No, what I think that's the point I'm trying to make. A forest is without time. If you take time into consideration, what I'm saying, time is movement. So if you make every tree move in either, a parallel up, down, left, right direction in a forest, you'll always bump into something. There's always going to be something somewhere. There's always...
Yes, but that's because you made trees compared to my eyeball.
No, I made trees compared to photons, as in they are always moving. There's always something in a space.
Okay, is there another galaxy within the 10 galaxy distances of us?
Within what?
Yeah, that makes no
Within
sense.
the
You just
distance of
asked-
10 galaxies. Like if
Is
you took
there
the width of a galaxy and you laid it out 10 times, is there another galaxy right there?
Are you talking spiral galaxy? Are you talking star?
Because in the
galaxy? Are
tree
you talking
example, that's
Andromeda?
what you're explaining.
No, I'm trying to simplify it.
No. The tree example is dependent upon distance. It's got nothing to do with how close they are. It's purely to do with the fact that you might have a massive gap between two trees here,
Right?
but because there is a tree further away
Right.
in that gap, it can be,
Right.
in that example, very, very far away.
Okay, let me change what I'm trying to say to you because I'm not saying it very well. Okay, let's say that I actually took a craft into outer space in an exact straight line.
Yeah.
Your point is eventually you will hit a star,
Yes.
no matter what
I
direction
believe
you
that
choose.
eventually you will hit a galaxy.
Whatever, you'll hit a bright stellar object of some kind.
Yeah.
Okay, I don't even care what it is. And I would agree with you.
Yeah.
But you don't get to use that because the appearance of that tree does not continue forever. Like light does not get to continue forever in all directions simultaneously as like some kind of a solid wave. It doesn't work that
Yes,
way.
it does. From the emitter. From a light, from the point at which it is emitted, it exists forever until it hits something.
Yes, but it would have to be a wave, not a particle. It'd have to be a sheet for you to be right.
Why?
It would have to be a sheet for the example to be accurate. It's not a sheet.
No, why? I don't understand why it would have to be a sheet. It spreads out in every direction.
Okay, it emits from every direction from the source. Is that what you meant?
Yes. But no, and
Oh.
it spreads out. It's described like a radio wave. It spreads out and gets weaker as it spreads out, or you receive less of it. Weaker is the wrong word there. So for every that's the cube. I think light uses the cube square law. So for every 1 unit, it spreads out 3.
Okay.
No, I'm bad at explaining this. Right, but the point being, it doesn't. The fact that you might only get 1 photon from that one star survive to hit you doesn't matter because of the sheer amount of stars that you will also get 1 photon from. Does that
I
matter?
think it would be the forest analogy would be better if the trees were exploding.
Or moving, like I said, taking time out of the equation.
I don't think why they need to be. I don't see why they need to be moving. You have them bloody well emitting light. There is no way you
Okay,
could hide.
Let's say they were exploding.
Yeah.
To say that I would see all, there's no path out. There's no lack of tree anywhere.
Yeah.
Is to say that all of the particles of all of the trees form a solid.
Yes.
No.
Well, no. The problem is you're half right and half wrong.
Okay, well, that's the part I'm objecting to in the tree example.
Richard, just to point out, you're asking Critical Cripple Dave to explain quantum mechanics and a lot of things.
It was his idea, not mine.
Okay,
No, it
well,
wasn't.
it may be his idea, it may not be his idea. I'm just pointing out, I watched an RI video today, Royal Institution video today, which is a history of quantum mechanics, and a guy who just wrote a book on quantum mechanics who admits that they use it like an iPhone and don't know how the iPhone works. Okay?
Yep.
So the people in this field have trouble explaining it to people, and you're asking Dave at 12 at night, who said he would not do this because he is very, very tired,
Yes.
to explain quantum mechanics to you. So
No, I'm not really quantum mechanics, only one function of quantum mechanics.
so just that one small bit of quantum mechanics. Dave,
Have you looked at... Okay,
Not all
let's
of
go
it.
the other way. Wait, you can go the other way. We can go the other way. Have you looked at the picture of the cosmic microwave background?
Indeed.
There are no gaps.
Nope. Differences
If
in
that,
temperature.
when that was emitted, that was in
then
the
why-
visible light range.
What are they calling seeds if there's no gaps?
The
There are points
level
of
temperature.
concentration.
Oh, there is a temperature difference of 0.3
decimal
degrees,
places.
and that
Whatever
map is
it
that
is.
all that's showing, right? But the point is, all of that is photons. It's at different temperatures. That's all. But it's coming from every direction.
Okay, then if we go into the right spectrum, it is a solid mass.
Yes.
Okay, so it always was a solid mass,
Yes.
which means
why?
the whole thing is static. So glad you agree with me.
No. Because it goes away when it all goes away.
No, you just
gonna
needed the
quote-
right camera.
There's an episode of Red Dwarf where time works backwards. That's all I can think of right now. That's all I can think of. Red Dwarf and time working backwards. The amazing Ford twins. That's it.
Don't know what that meant, any of it. Sorry. Love you.
That's a shout out to Dave. Dave, you're Red Dwarf. Come on. Crichton. Yes? What?
Yes.
You do,
But
don't you?
backward- The Amazing Brothers were brilliant.
See, he fucking knows. This is why we love Dave. We need more Dave. We need more.
Nod Null. We're going to Nod Null in April.
Pardon? Nod nod.
We're going to Nod Null in April.
Nod nod.
Yep.
What the fuck is nod nod?
It's Bulgarian.
For Dave Con. It's not named after you, but the entire
No, it's
weekend.
not. No. I'll let Nerdy explain. I've got to go to the loo.
Yes, we're going to end this now anyway. We've been having fun. We're going to end it now anyway, because Critical did say he would not do this. And then
Yeah, we got to cut him off because he won't quit.
Yeah. He has one of
Okay,
those
let's cut him
brains.
off.
He's one of those brains. No, I can't cut him off. He'll ruin the scene.
Yeah.
Everybody.
Yeah. Well, I'll help by saying I love you all, peace and respect to you all, and good night.
Good night.
Richard,
Good night.
thank
I look
you.
forward to the day that we're all great friends. Have peace.
Discord. Oh, God. Anyway, yes, everybody. Yeah, I don't know what we were doing. It just became something. And yeah, thanks everybody for turning up. More Dave. More Dave. I'm going to spend all of tonight redoing all my scenes to include an extra person. Dave. Dave. Type 1 for more Dave. Type 1 for more Dave. Type 2 for no more Dave. And type 3 for give me Nerdy. Nerdy sounds cool. We've got a 3. You're only typing 3 because you're ahead of the chat by 15 seconds, Dave. That's a cheat. That's a fucking cheat. If, yeah, anybody wants to, the Discord link is in the description. We'll all be in the Pigsty Discord. So, yeah, we'll see you all there. And let me see. I'm not going to fuck this up. I'm going to take my time. Dave, everybody sub to Dave. Dave's been playing with OBS. Okay, Dave's working on something. There's something going on. It's not a sub to Dave. Okay, his name's in the chat. Click it. go to channel, sub to Dave. Sub to Dave. Everybody, Dave, fucking say something, man. You're leaving me hanging here. I'm looking for the right scene. Talk to the people. There we go. Everybody, bye-bye.
Bye.